So after watching this video of kinesin, of a single kinesin molecule walking along a single microtubule polymer molecule, uh, what you'll see in the caption is that the velocity is calculated to be 600 to 1000 nanometer per second. And there's also artist rendition of this going around, and a video that is about 7 minutes long. If you haven't watched it before, I encourage you to watch that video too. And I have a question. How do you think this velocity is measured? So if you are watching this by yourself and not in a classroom, then I encourage you to pause the video and think about the question a little bit and take notes and send the answers by email, or later I can post them, I can discuss them as a discussion forum online or something like that. Um, and in these slides, from time to time, there will be questions, and they will be numbered so that you can discuss a particular question. So here's another question. How fast does Usain Bolt run? So what I want you to compare is how these velocities compare to each other, compared to the size of the thing that is moving, in this case Usain Bolt, and in this case a kinesin molecule. So so are they comparable velocities if you consider the size to velocity ratio, or is it completely different? So I'd like you to think about that a little bit. Now I'll move on to part 2 of this lecture, classical and continuum mechanics. If you haven't taken a physics course before, or even if you had and it was a long time ago, for example before summer, then it might jog your memory. So classical mechanics. So classical mechanics, one of the giants of classical mechanics is Sir Isaac Newton, and everyone here should know about Newton's laws of motion. So often classical mechanics, or mechanics in general, is divided into statics and dynamics. So statics is why things don't move, or study of things that are not in relative motion, but they could be applying forces on each other. And dynamics is when they're moving with respect to each other, and if they're moving, then how they move. So you can relate that to Newton's laws. For example, Newton's second law talks about how a body can accelerate if a force is applied to it. And many times in classical mechanics, people restrict to rigid bodies. So the rigid body, what is a rigid body? So a rigid body is a idealization of a hard object that is difficult to deform or change in shape. So early on, people found it difficult to think about things that change shape. So they said, let's consider it in the ideal case that it doesn't change shape and just moves or rotates from one place to another. And then they developed all this mathematics to describe those bodies. And for example, there's a book on statics from 1891. It's called The Elements of Statics and Dynamics, and it talks about rest, force, and rigid bodies and particles. So a rigid body can often be idealized as a point mass. So as if all the mass in the body is concentrated at one point. Where could that be? So for those watching on the web, I'd like you to think about the other questions. 1.4, can you think about rigid bodies in the human body and organs that are not rigid? And what about fluids? Are those rigid bodies or are they something else? And so this is a book. On the right, you see the book is from 1891. So what do you think had changed from 1891 or the 1800s to now in terms of classical mechanics? So I'm not a physicist, but from the engineering point of view, not much had changed in the fundamentals. So the fundamentals are still the governing equations. Everything is still based on Newton's laws of motion. But now we're able to solve more complex problems, while previously we were only able to solve a very restricted set of problems. So people have had more time to think about how to apply these laws to specific situations. And we're now able to solve much more complex problems, also because there are computers, but also because people have had a longer time to think about those issues. So the basic governing equations are the same in classical mechanics, and it's mostly based on the Newton's laws of motion. Now, um, oftentimes in a introductory mechanics course, for example in physics, people will not go directly into continuum mechanics because it's much more complex mathematically than classical mechanics. However, in biomechanics, we tend to introduce the student to continuum mechanics sooner. So what is continuum mechanics? So according to Wikipedia, a change in the configuration of a continuum body, so any body that you can think of, results in a what can be called displacement. Now the displacement can be compartmentalized or can be um, separated into two different phenomena where the body has moved as if it's a rigid body and then it changes in shape. So in classical mechanics, you usually restrict yourself to the rigid body displacement problems, while in continuum mechanics, you are looking at the deformation of the body. So the rigid body displacement can consist of a translation as well as rotation in three-dimensional space, while the deformation implies the change in shape or size of the body. So the body can shrink, expand, um, or it can bend, it can twist, and so all that has to be taken into account when you are talking about the mechanics of soft materials, because in hard materials it's still there, but it's so small most of the time compared to the displacement itself that it can be simplified uh, into a linear relation, or it can be ignored at many times. Even when you don't ignore it, you can consider it in a simpler formulation. So let's look at two examples of linear equations in mechanics. So one of the classical equations in classical mechanics is F equals to ma. Um, and can you think of a linear equation that describes deformation? For example, change in length. So here's a spring, and when it's no mass is attached to the spring, it has a zero displacement, and you attach a mass, and then it moves, it stretches a little bit, you attach more mass, and it stretches more. So can you describe an equation or name the equation? So the equation in question, the equation that I talked about in the last slide is Hooke's law. And Hooke's law can be thought of as the beginning point of continuum mechanics. So Hooke's law is often written as F equals to minus kx. So you can see there is F equals to ma and F equals to minus kx. So are these two things the same, or are they different? And you can see in one case that there's no negative sign, while in Hooke's law there's a negative sign, while the constant of proportionality between force and acceleration is positive. Can you think of why that is so? So this ends part 2 of this lecture, and the discussion points on the questions I'll be posting separately. In part 3, we'll be looking at viscoelastic models.